and we hope to have those done early this week. They're mostly looking pretty good. They were easy exercises. They were intentionally easy, because these exams aren't designed to be gatekeeping, like to kick people out. They're designed to be a confirmation that you've picked up the material as we've gone along for these first 4 weeks. Do understand, though, that we're going to get into more complex topics, and today exemplifies that. We're going to start talking about pointers in C. So understand that the course it builds on each other, so necessarily it gets more challenging as we go along. Any questions? Otherwise, remember, we're getting back into the routine. We've got your reading due today. You've got your lab due on Tuesday, and then you start your hack on Thursday. And we'll have that same routine now until the midterm. We'll get back into the same routine until your next exam and then your final exam. Right? So to get back to what we were doing over a week ago, we were looking at functions and creating our own functions. And the way we left off with talking about how functions actually work. That when a function calls a function, that we've got this thing called the call stack. And it's a stack, basically, of dishes. If I've got a function called main, everything will have a function called main. It has its own local variables, its return value, and stuff like that. When it calls, and I think that this is the example that we did, when it calls the average function, right, then a brand new stack frame is created with its own local variables and parameters. Then if that calls another function, then a new stack frame is created on top of that. As functions return back from the called functions, if they return back to the called function, then each one of these stack frames is destroyed and popped off the top and destroyed. All right? All the variables inside there are no longer available. The return value is returned back to the calling function, but that's it. All of these variables are gone. Right? So let's take a look at another example here. We may or may not have done this example, I forget, but let's go ahead and retread it. Where in main here, I've got two variables, a and b, 10 and 20. And then I print them out. And of course, it's going to print out 10 and 20. And then I make an attempt to call this function called swap that takes a and b and attempts to swap them around. It does that, the first thing we do in the function is verify that we receive 10 and 20. Then we put a into a temporary variable. We put b into a, and then we take that temporary variable and put it into b, and thus we've actually swapped them. On line 6, we should see 20 and 10. But when we come back from the function, what are we going to see on line 16? Right? So think about that in the back of your mind, and let's see it actually execute here. So 10 and 20, a and b, in the main. We print them out, and indeed we do get 10 and 20 up here. But when we call the function, a new stack frame is created on the top. Now, this visualization grows down. It doesn't matter. You can turn your computer upside down, right? It's not really up or down, right? It's different areas of memory. But we've got our own copy of a and b in this function here. We've got our own stack frame with its own a and b. Is that the same a and b as up here? Certainly not. They're different boxes, right? You might have John and Jane living in one house and a different John and Jane living in another house, and they're certainly not the same person. Or they're certainly not the same people. So inside this function, when we receive the values 10 and 20, we do successfully swap them out. Right? You see now 20 and 10. So when it gets printed out, 10 and 20. But did you see any changes with the original variables in main? Nope. So when we return and that stack frame gets destroyed, the swapped a and b are gone. The original a and b remain, and we've got 10 and 20. So our swap function didn't work here because it operated on copies of those values. That's called pass by value, right? So here's the example that I've already put into our notes here. Now let's make some observations, right? The values of the variables a and b are passed to the function. Right? More precisely, copies of the variable values are passed, not the variables themselves. So inside the function, the swap only applies to the copies, not the originals. To drive home that point, let me come back here and edit this code. What if I called them not A and B, but X and Y? Is it absolutely clear now that these are not the same variables? Of course, I would have to go ahead and change all the rest of the code, right? I just used A and B to kind of obfuscate the idea that these are not the same variables, right? The function has its own copies, and the original function main has its own copies, right? This is known as passing by value, right? Values of the variables are copied onto the call stack and passed to the function, right? Just like over here, right? The arguments A and B that are given to the sum function and the arguments A and B that are given to the average function that originate from the main being having values n and m, right? Those are all three sets of completely different variables, right? You are passing in copies. And so when you change the copies, it has no effect on the original variables, right? Changes to the copies have no effect. No effect on the original variables in main. Right? But I really want to swap variables. Right? I really want to do this exercise. So to do that, we're going to have to introduce a new tool called pointers. Right? Pointers. So everything in a computer is stored in memory. Right? That's why we just call it memory. It remembers these things. Everything, in particular, data is stored in a computer's memory. Right? Memory has two parts: an address and contents. Right? So here's a visualization of that. Right? So the address here is usually given as a bunch of hexadecimal numbers. Why? Because it's just a number. It's relevant to the computer, but it's not relevant to us, right? If we were to think of these terms in terms of physical addresses, right, going to 1234 ABC Street, South ABC Street, right? That's just a number that somebody assigned to that place so that you could actually find the place on a map. These are just numbers over here, addresses, so that the computer can find that variable stored in memory somewhere. Right? The addresses are completely meaningless to us because it could be that the program is loaded up in one area of memory on one invocation on one run, and then it's loaded up in a different part of memory in a completely different location on the second run. Right? What matters to us is the contents. Right? So, for example, if I store pi in memory, it's going to be stored at some address, and it can be accessed by the computer by looking up at its address because it's keeping track of that stuff. Right? The content is what's relevant to us. We can set that int a is equal to 42, right? And that ends up being in the memory somewhere. Right? Where in the memory? That's where pointers come in. Right? So regular old variables correspond to the contents. Pointer variables can hold an address, or memory location, or reference. We'll use all these terms interchangeably. We call them pointers because they literally point to a location, right? We've got this reference to this memory location over there. It says, where is this variable stored? And it points, it's over there. Right? Go look at that house over there. Go look at that area of memory, and that's where you'll find it, okay? So C is unique in that it allows you to create variables that are pointer variables explicitly, and it allows you to manipulate low-level memory, like you can directly manipulate the contents of memory. Not a lot of programming languages do this. In fact, C, C++ are two of the primary languages that I know of that allow you to do this, but the vast majority of programming languages do not allow you to do this. And it's because with great power comes great responsibility. It is very, very difficult to make sure that you are managing your memory correctly. Right? Most programming languages shut this ability off to you, but it comes at a cost, either through efficiency or through less flexibility. There is great power here with pointers because you can directly access and manipulate the contents of memory, including your own program, right? Because everything is stored in memory, including your program. Right? Down here at the bottom of the call stack, what gets loaded up first? Your program, right? And then global variables, static content, and only then do we create the first stack frame corresponding to main. Right? So how does this work? To do that, I'm going to go back to our IDE here, okay? And I'll embed all of our comments here, all of our notes as comments as we go along. So you can create regular, is this big enough? That's too big, there we go. You can create regular old variables as follows, right? You know how to do this already. This is what you've been doing in the first 4 weeks. I'll go ahead and create an integer variable here and set it equal to 42. I can create a double variable, right? And say pi is equal to 3.1415, right? Those are regular variables. Now what we want to do is we want to create a pointer variable that can point to an integer. Right? To do that, I use the brand new syntax, int star, and I can't call it a because I've already used that variable name. Instead, what I'm going to do is I'm going to make it point to a, so I'll go ahead and call it ptr, pointer to a. Right? So int star. Now, white space generally doesn't matter, so you could write it like this. You could write it like this. You could write it like that. I'm going to write it like this and stay consistent. Right? As long as you stay consistent, however you write it is up to you. But I'd encourage you to do this. Right? It's a different type. It's not an integer, right? Pointer to integer is not an integer, right? Pointer to a is a pointer to an integer, not an integer itself. Right? It's the difference between these two numbers. If I store 32,321,231, that's the integer, right? That's a regular old value. The memory location at which it's stored is this random hexadecimal number. To show you the difference, first of all, I need to actually make it point to something. By default, there is no value associated with uninitialized variables. Go ahead and spell check that for me. Right? Just like if I create int a or int x, what value is stored in x as of line 13? Who knows, right? It could be 0. It could be garbage. It could be dead beef. Right? What value is stored in pointer to a at this point? Same answer. It could be 0. It could be garbage. It could be dead beef. It could be pointing to a memory location that doesn't belong to my program. And if that's a memory location that doesn't belong to my program, what do you think happens when I try to access it? Hopefully it segfaults, right? It segfaults because the operating system says, you're trying to access memory that doesn't belong to you. That's illegal. I'm going to segmentation fault that. You tried to access a segment of memory that doesn't belong to you. That's a fault. That's a bad thing. And it kills the program with a segmentation fault. Imagine if you were allowed to access arbitrary memory. Right? You could access the operating system's memory. You could access memory that belongs to another program of another user on the system that stores passwords or something. Right? That's a huge security risk. So, by default, there's no value associated with it. You can make a pointer point to nothing. So there are going to be several notions of nothing in this course. 0 is nothing, right? If you try to parse out a to I of a hello, right, you end up with nothing because there is no numerical value there. The value of nothing is 0. Here's a new idea of nothing. Pointer to a is equal to null. It is defined in the standard library. It is a keyword, or a reserved word at least. NULL, all uppercase, and written like that. It is case sensitive, so lowercase NULL. Some programming languages do that, Java, for example. But C, it is all caps, null. Right? The null pointer is the nothing pointer. What does it point to? It points to null. It doesn't point to anything. And you can check for that, right? If pointer to A is equal to null, right, then printf error cannot access that memory. Right? In fact, if you tried to do something with it, again, segmentation fault. It's a non-existent memory location, okay? You can, but should never, no, never mind. I'll come back to this, all right? We'll come back to that later with pitfalls, right? So what I want to do is we want to make pointer to A actually point to the variable A. To do that, I could write this. Pointer to A is equal to A. That would be wrong, though, right? What is the thing on the left-hand side? It's a pointer, right? It's a memory location. It is one of these things, these hexadecimal numbers over here, right? What is the thing on the right-hand side? That's not a pointer. That's a regular old variable. Are these two the same thing? Nope. One's an address and one is a value, right? So how do I make this regular old variable into a pointer variable so that they match? I need another piece of new syntax, the ampersand. That looks mighty familiar. Where have we seen that before? In scanf, right? In scanf, you put the ampersand in front of it to get the memory location of that variable so you can hand it off to the scanf function. We'll understand why here in a moment, but now it's a little bit demystified. Before we were saying that's magic, don't worry until later. Now we know what it is. It gets the memory location, right? Ampersand in front of a regular old variable gets the memory address of that variable, so that we can make a pointer point to that memory address. Right? I think I've got another picture here that I can share. Where's my pointer? Nope, not that one. Yep, here we go. Here's an example. Now I've abbreviated this PTRA instead, right? Somewhere in memory, there's this pointer being stored, and I set it equal to null. It's not pointing to anything. But after I use the ampersand on A, it now loads this up with its actual memory location that it points to. See that memory location, that memory address? Right? That's the value that the pointer receives. And it's pointing to this value 10 over here. I used 42 though. Right? So that's why we literally call it a pointer, because it is a value that points to a memory location. Okay? Let's print it out and see what happens. Right? So let's print some information here. A is a regular old variable. It holds the value %d and the line, and then I'll print out A. Right? Printf, pointer to A is a pointer and has the value ... % something, pointer to A. Now, it's not an integer, so I can't use %d. It's not a floating point number, so I can't use %f. It is a pointer. So what do you think the placeholder should be? It does make sense, by the way. P for pointer. Printf. The memory location, %p, holds the value ... pointer to A. Right? That's the memory location of A, and it holds the value A. Right? We'll come back and change that here in a moment. Let me go ahead and compile this and show you what it looks like. Oops. Pointer. There we go. Did I spell it right there? Yeah. Oh, too few arguments. What's wrong? On line 34. No, there. Oh, that's right. And holds the value %d. There we go. Okay, let's run this. Cannot access that memory. Why? Because it's null up here. Right? A is a regular old variable. It holds the value 42. Pointer to A is a pointer and has the value, this random memory location. Right? In hexadecimal, it's 7FFF AA BD BA 64. Right? And that memory location corresponds to the value 42. Just like this picture over here, but instead of 42, it's 10. And instead of this random memory location that I put into the figure, it's this memory location over here. Now, if I ran this again, would I get the exact same results? No, why not? Different memory. Yep, it is different memory, right? Do you see that? It ends in, the original was A64, and this one is 024. That's because when a program gets loaded up in memory, the first thing that happens is the program code gets loaded up. It gets loaded up in different parts of the memory every single time, right? Because there's always stuff running on the computer. The programs are coming into existence and dying and every microsecond, right? So memory is being used, and then it's not being used, and then it's being given back to the operating system, and this is all happening millions of times per second. So the likelihood that your program gets loaded up in exactly the same spot every single time is extremely small, right? That only happens when you really, really manage the memory, right? Okay. Yeah, go ahead.
Can pointers have a scope?
Same scope. You might be asking, can you do something like this? Pointer to A. I'll make it point to the memory location 432. Now, is that likely to work? That may or may not be a valid memory location. It may or may not belong to me. But if I try to do something with it, bad things are going to happen. All right? And we'll formalize that here in a moment. But otherwise, the scope of a pointer is the same as wherever you declared it. Here I declared it in main. Pointer to A only exists in main. And that's it. It can point to any other part of your program or memory that your program allocated or something. We'll look at that later. But same scoping rules as everything else. Okay. Once you have a pointer to a memory location, you can manipulate the contents of memory through the pointer. So for example, if I wanted to reset A to be 10, I could do that if it was just a regular old variable. I want to do that through its pointer variable though. Pointer to A. Right? If I did this, interpret that for me. It's the exact same interpretation I just gave you. Pointer to A. It's a pointer. If I set it equal to 10, where is it pointing now? To memory address 10. Is that likely to belong to me? Nope. Right? So what I want to do is I want to dereference this. Right? So you can take a pointer variable and turn it into a regular old variable. That is temporarily. Yeah, I'll emphasize that, temporarily. So you can set or modify its contents or access them. Right? So the dereferencing operator here, dereference, to dereference, use the star operator. It's not start operator, the star operator. Right? It's the exact same syntax as we use to declare the pointer variable. That's an unfortunate, not coincidence, but when they came up with this idea, they just thought, oh, we'll just use the same thing, right? Star and star. One is a declaration, one is a dereference. So it takes a pointer variable and turns it into a regular old variable so that you can then assign the value 10 to it. Right? I've got a picture for that too, I think. Yep. Right. So there is the process of dereferencing. If I've got a pointer and put a star in front of it and set that equal to 20, it goes to the memory location stored by the pointer, jumps to that memory location, and changes the value to 20. Right? But only because I put a star in front of it, making it a regular old variable. Right? So it's unfortunate, but that's something that we'll just have to get used to and memorize. How do you go from one to the other? Right? In fact, let's go ahead and put that in the notes right now. So observe. Right? You can take a regular old variable and get its memory address pointer using the referencing operator, which is the ampersand. Just the opposite, you can take a pointer variable and change it to a regular variable using the dereferencing operator. By the way, again, these don't change the variables. They're still pointers. They're still regular variables. It's like typecasting an integer, one of the integers, so that you can divide an integer by an integer, right? It temporarily, for the purposes of that operation, changes the type of the variable. But the dereferencing operator is the star operator, right? Or asterisk. Right? It just takes some getting used to remember which one is which. If you want a helpful hint here, if I went back 20 years and remembered my calculus, right, I could never remember what the derivative of sine is. Anybody know what it is? Cosine, right? Well, then what's the derivative of cosine? Negative sine. I always got those backwards, right? I never remembered which one was minus and which one was plus. So all I did was put it on a Post-it note, put it above my desk, and all I ever had to do was look up at it, right? Now, when it came time to a test and you were forced to memorize, I don't know if you're forced to memorize stuff like that still, probably, unfortunately. But in this class, you're never forced to memorize anything. Take that Post-it note, leave it there until you drive it into your brain, right? To this day, 20 years later, I still don't remember which one was negative and which was positive, right? That's why I relied on you to tell me, right? It's not something that you need to memorize. This is not something that you need to memorize. You will eventually memorize it by simply doing it over and over again for the rest of the semester, right? But if you need to, put that on your Post-it note and put it up on your computer, which one is which. The ampersand takes a regular old variable and turns it into a pointer variable. The opposite, pointer variable into a regular old variable, is the dereferencing operator, the star operator, right? So again, you don't have to memorize that stuff, okay? All right, so let's see. More observation. Let's go back to the notes. Actually, what I'm going to do is I'm going to make sure that you have all of this in the notes. There we go. And see, there we go. There. All right. So why is this important, right? Why manipulate a variable through a pointer when you could just write x or a is equal to 42 or a is equal to 10? Why do you need pointer variables? Because it now solves our original problem over here, right? Let me go back to our Python tutor and let's change this program now. Right? So instead of passing it by value, copies of 10 and 20, what I'm going to do is I'm going to pass in the memory address of a variable, right? And I'll rename them A and B here. A and B, right? Okay. And let's go ahead and get rid of this print statement and this print statement. And let's just focus on the code here for a second, okay? Now, I've been given the memory addresses of where these things. That means I can go to their house and I can rearrange their furniture, right? If I have the address, I can go to jump to that memory location and I can change the contents of that memory, right? Whereas before I couldn't do that because these were just copies. Right? I can change the copies, but I can't change the originals. Now that I've got the addresses of the originals, I can change them. Tell me what line 3 should look like now. The thing on the left-hand side is a regular old variable. The thing on the right-hand side is not a regular old variable. How do I take that pointer variable, change it into a regular old variable, so that I can get 10 out of there and put it into temp? Which one was it again on my Post-it note that I put above my desk? Right. Asterisk, right? There we go. How can I dereference A so that I can grab its set its value to the value stored pointed to by B? Dereference, dereference. And finally, dereference. Right? And then return. There was no explicit return statement here, but there you go. Right? I'll go ahead and leave it there. You should have it, even if it's not necessary. Now let's come over here to main, where I've got A and B, which are regular old variables. Right? If I print them out, they won't be swapped. Before the swap function, of course, they'll be 10 and 20. Now, if I'm passing in the memory addresses, and you can jump to those memory locations, pull out 10, pull out 20, and swap them around, it should actually work now. But am I passing regular old variables to swap anymore? Nope. How do I take a regular old variable and turn it into a pointer variable that this function expects? What's on your Post-it note? An ampersand. Ampersand A and ampersand B. Let's visualize this execution now. As it takes a couple of seconds, there we go. You'll actually see what the pointer looks like in this visualization. A and B, 10 and 20. We print them out, and we get 10 and 20 just as before. Now, when we jump to the swap function, you'll note here that these are not integers. A and B are no longer integers. They are pointers to integers. Next. And they point back to the original values in the other stack frame. We can jump to those memory locations by dereferencing them, as we're going to do in line 3 and 4 and 5. Right? It jumps to A through its pointer, takes the value stored in there, and then places it in a temp down here. Likewise with the others, it jumps to that memory location and changes the value to 20, and then jumps to that memory location and changes the value to 10. So that when we return back from swap, after that stack frame gets destroyed, look at that now. The original A and B are now successfully swapped, 20 and 10. When it gets printed out, they are indeed swapped. Right? So this allows us to pass by reference instead. This is what this is referred to as, right? So observations. Using pointers, come on, jump down there. There you go. Using pointers allows us to pass by reference to functions. Right? Instead of copies of values, we can pass in memory locations, addresses, and a function can manipulate the original variables. Right? Now, our swap function works. Right? This is kind of a toy example to get the point across here, but we will quickly get into some real examples. In fact, our first real example is scanf. Remember, scanf. Scanf required that you use the ampersand to pass in a variable. Why? So let's go back over here to our demonstration. This is already in the notes, so you're good on that. Int x, and then we call scanf %d, and then pass in x. What's going to happen when I try to compile this with everything turned on, all the warnings on? It's going to say, nope, that's an integer, but it expects what now? Int star. Demystified. What is an int star now? We know what that is. It's a pointer. It expects a pointer. Why? What would I be doing if I didn't pass in the pointer here? I'd be passing in whatever is stored in x. 42, right? Can it do anything with 42? 42 is not a valid memory location. It needs to know, look, I'm going to go to the standard output, or the standard input, the keyboard masher, right? The ID10T user that's mashing the keyboard there. And I am going to scan their input, and if they typed 123, I've got 123 now. Where do I put it? I put it in that memory location over there. Right? And so I need to know where's the memory location of the variable that you want this value put in. How do I do that? Through a, what am I doing? Well, this is pointing. I'm pointing to that memory location over there. Right? Put it over there. Put the results into that memory location over there so that I have access to them when I get over here. Right? Only ampersand will work because ampersand gives you the memory address of that variable so that you can pass it by reference. There's our first real use case for this. Right? In order for scanf to work, it needs to know where to put it. Right? And if it doesn't know where to put it, then you can't get your answers, right? You can't get your input from the user. Right? All right. So passing by reference means that you can give a function a bucket in which to put a result, right? Like scanf, rather than a copy of a value that is not useful. Right? I don't care that it's 42, right? That's not a memory location I've ever used. It's not a memory location that maybe even exists. Right? Generally, they're unsigned, so if I gave it a memory location of -10, right? Nope, that's not correct, right? It might as well be null, right? All right, so there are some observations. Now let's talk about some pitfalls. Right? You you should the first one is you should always initialize a pointer. All right, to null if nothing else. All right. Otherwise, uninitialized pointers may point to anything. All right. Let me show you the consequences of that. So let's go ahead and create an integer variable here. Int x is equal to 42. Let's go ahead and create a int star pointer to x. Right? It's not necessarily pointing to anything. It could be pointing to dead beef. Let's go ahead and try to access it, pointer to x, and set its value to 101, and then print it out. Printf x now has the value %d and the line x. All right? I've got a regular old variable, 42 here. I've got a pointer to x, but I've never actually made it point to anything. And then I attempt to dereference it and set it equal to 101. Let's find out what happens here. Right? First of all, a warning. Right? If I didn't do the wall flag, I wonder if it would nope, wouldn't warn me at all. So thankfully, it is warning me if I turn on all the warnings. Right? There's an uninitialized pointer. I don't know what's going to happen here. Let's find out. Do you remember what happens when you forget the ampersand in scanf, in addition to this warning here? What happens to your program? Look familiar? Segmentation fault, right? Attempting to access an invalid pointer of memory location. I have no idea what this memory location is. In fact, we can print it out. Right? Pointer to x. Oops. Pointer to x points to %p and the line. Pointer to x. Right? Let's find out if this even points to something. Right? Yeah. Warning, warning, warning. Ah, it doesn't even get to print that stuff. Actually, let's put it up here. Do that, and then pointer to x is equal to 101. Let's try to print it out before we actually use it. We might get away with that printing there. We did. It points to nil. So yet another yet another concept of nothing. Nil, right? That's just its interpretation of what value is stored there, right? Apparently, it does end up being 0, right? It's equivalent to setting it equal to null, right? The same thing will happen here, by the way. If I try to, nope, yeah, let's do it this way. Pointer to x, dereference it to set it equal to 101. What I'm doing here is dereferencing a null pointer. Yep, it's complaining, but it's going to let me do it. And it's definitely a segmentation fault here as well, right? Because you're pointing to nothing. You can't put something into nothing, right? And so it ends up as a segmentation fault. Nor should you do something like this. Pointer to x is equal to 101, right? 101 is not a memory location that belongs to me, right? I could probably print it out, and it would probably work, but it's still going to seg fault on line 21. Nope, it's seg faulted even before that, right? Yep, let me move it down here. Come on, at least let me see the memory location of it. Nope, it's not even going to let me do that. Yep. Oh well, yeah. Oh, thank you. There we go. Now it should at least let me print this stuff out. I'm printing it twice, though. Don't need to print it twice. Dereference there. That's what I wanted to do. There we go. And then a dot out. Pointer to x points to nil. Segmentation fault in trying to set its value, right? Because it's pointing to null. Right? It's pointing to nothing. Okay. How do we make it point to something? Ampersand and then that something, and that will work. Okay. So, uninitialized pointers may point to anything. Another pitfall, you do not assign a literal value to a pointer. Right? For example, if I did, say, int star ptr is equal to 101. Right? This makes it point to memory location 101, which likely does not belong to you, resulting in a seg fault. Another pitfall that you don't want to do is you want to make sure that you are making like pointers point to like things. Integer pointers should point to integers, and double pointers should point to doubles. Right? What if you don't do that? Right? Well, let's take a look and see how you could do that. First of all, let's get rid of all this. And let's go ahead and make a double. Pi is equal to 3.14159. There we go. And let's make a pointer to pi. Double pointer to pi. Well, is that a pointer? Nope. What do I need to make it into a pointer? Star. And now I can make it point to pi. Right? And I can change pi. Right? I could say that pointer to pi is equal to 3.14 instead. Of course, I would have to dereference it to make it into a regular old variable. Printf pi is now %d f and the line pi. There we go. It's now 3.14 instead of the original value. Right? And just a note here, I am using this pi as as an example. Do you ever actually use your own definition of pi? Nope, not a good idea. Instead, what should you do? Use MPy in the math library. We saw that a lot on the exam. People just defining their own pi and then getting garbage results in the grader because they were using an inaccurate version of pi like this, right? Or even worse, this. Right? Okay, what if I made an integer pointer point to pi? Int star ptr, and I'll make it point to pi. What's going to happen here? Truncation, maybe? Segmentation fault, maybe? Bus error of some sort? I don't know. Let's go ahead and see what happens here. Printf ptr points to %p for the memory location and has the value %d because, of course, it's an integer now, right? So we've got ptr and dereferencing ptr. Okay? PTR is the pointer. That corresponds to the memory location. Dereferencing PTR is the integer that supposedly it points to. So if it's integer truncation, we would expect that it's 3. Let's find out. First of all, warning, because you shouldn't be doing this. There. Is it simply integer truncation? Nope. Remember back to your second lab. You ran a program that we wrote for you that output how many bytes each type takes. Does anybody remember how many bytes an integer takes? 4. Right? 32 bits, 4 bytes. A byte is 8 bits. A bit is a 0 or a 1. Right? Don't worry about the low-level details. You'll do that in, say, computer architecture. Right? So an integer is 4 bytes. How many bytes do you think a double is? Hint, strong hint, it's in the name. 8, right? Because it's double precision, right? So when I have a pointer, there's pi stored in these 8 bytes right here. When I have a pointer that only points to the first 4, is that going to work? No, it's going to point to the first 32 bits in pi, which, when interpreted as an integer, is this garbage right here. It's not an integer truncation of, oh, it's just the wholesale 3 value. No, it's taking whatever bytes or bits are stored in this memory location and saying, there's my number. That number happens to be 134389535. Right? It's just random. It's not random garbage, but it is garbage. Right? So make sure that your integer pointers point to integers, double pointers point to doubles. What about a character pointer? Ooh, that's interesting. Char star, foo. What is that? And in fact, that looks familiar. Char star. Ignore the other parts for now. What is that? It's a pointer to a character. It's not just a pointer to a character, it's a pointer to an array of characters. H-E-L-L-O, right? A string. Right? We'll get into that later. But what is this thing now? Char star star. What do you think 2 stars is? If 1 star is a pointer, What's 2 stars? It's a double pointer. It's a pointer to a pointer, and that pointer points to something else. Right? In this case, it's pointing to one string, multiple strings. So think of it in 2 dimensions. You have a matrix. The first one is hello. The second one is world. The third one is whatever, right? String, string, string. This is an array of strings right here, right? And we've been partially demystified because now we know what pointers are. Yeah, question? Or no?
It's another question in probably, Joe. If there were 3 stars, would you have, because it's
Yep.
like dimensions, would it be a 3-dimensional?
It's a 3-dimensional thing. We call those rows, columns, and aisles in the 3rd dimension. You can do 4 dimensions. You can do 5 dimensions, 6 dimensions. You can do as many dimensions as you want. Not a good idea. Right? Keep it simple. Probably 2 dimensions is certainly the highest that we'll go up to in this course. If you want 3 dimensions or more, you're shopping at the wrong store. You shouldn't be shopping at the pointer store. You should be shopping at the structure store, which is something that we'll look at the end of the course, right? Defining your own types. Okay? All right, so integer pointers should point to integers, double pointers should point to doubles, or you get weird, undefined behavior. Right? So make sure that you're pointing things to pointing, right? To the things that they should be pointing to. Right? So in summary, a pointer is a memory address or a reference of a memory address. A pointer variable can be declared using the syntax int star or double star or char star or whatever. It's best to initialize pointers to null or you will have a bad time. To make a pointer variable, a regular old variable, use the dereference operator, the star. Right? To make a regular variable into a pointer, use the referencing operator, the ampersand. Don't make pointers point to things that they shouldn't point to. Again, this all goes back to with great power comes great responsibility. Right? You have a lot of power here because you can directly manipulate the contents of memory, including your own memory, including other programs' memory. Right? And with that power comes the responsibility not to do stupid things. Right? One last thing. I don't know if the sound will work here, but on YouTube, Bret Hart pointer. So Bret Hart was this wrestler back in the 80s. And in the 80s, there was this video game that they developed for WWF or something like that. And as a promotion, they got a couple of the wrestlers to go in with the actual developers, and they just shot these stupid scenes. And I have no idea if this is going to work or not, but remember that if you get a segmentation fault, remember what Bret Hart says.
Come on, you guys. There it is, right there in front of you the whole time. You're dereferencing a null pointer.
You're dereferencing a null pointer, you idiots. And then his colleague whacks him upside the head. Right? So remember Bret Hart if you ever get a segmentation fault, and whack yourself upside the head. I dereferenced a null pointer. Right?